It is a pleasure to give this talk on AI, its present and its future. And to start, I will say that today there is a great deal of confusion about what is the ultimate goal of AI, and opinions are divided between two different positions. Some AI research and companies believe that it is artificial general intelligence. This is an ill-defined term that suggests that it can be achieved through machine learning and its further development. So machine learning is the end of the story. And other people like me believe that the goal of AI is to build machines with human level intelligence, which of course requires an agreement on what intelligence is, but this is not a problem. You can find definitions in dictionaries that existed before AI, and you will see that it's the ability to learn, understand, and think about the world, and the ability to do this well. Of course, machines can do impressive things and outperform humans in particular tasks, but they cannot surpass humans in situation awareness and also creative thinking. And of course, it's clear that without an idea about what intelligence is, we cannot develop a theory of intelligence. And now, in my opinion, AI is still in its infancy, and it gives only the elements to build intelligent systems. We don't have the principles how to build complex intelligent systems, and AI today focuses on conversational systems. And I think that in the future, we need other types of systems. We need the monitors that will allow predictions and understanding situations. So we talk about predictive and analytical AI, and of course, we will need end-to-end controllers for autonomous systems. So I believe that the AI industry revolution has only just begun, and its realization will depend on our ability to develop these three types of systems. Something else that is important is discussed a lot is the validation of AI systems. Today, we know that AI systems are black boxes, and this raises questions about the trustworthiness. There is a lot of discussion about safe AI. This has been the subject of international summits. And of course, safety is a general concept. We need to specialize it. We don't know what is safety for LLMs or safety for self-driving systems. In addition now to technical properties like safety or security, there is a lot of discussion about human-centric properties. We find papers talking about responsible AI, AI aligned with ethical values, human values, or there are papers that attribute mental attitudes to AI systems. I think that all these works lack foundation because they ignore some very basic epistemic principle. If you claim that the system satisfies a property, then this must be backed by a rigorous validation methods. Something that I'm going to discuss in this talk, whether it is possible to guarantee properties of AI systems and what we can learn from traditional systems engineering. This is an outline of my talk. I will discuss autonomous systems, validation of AI systems, and talk about the future. Now, autonomous systems are, in my opinion, the ultimate stage in the evolution of AI. They are distributed, the real-time systems. They are made up of agents, each agent pursuing specific goals. We talk about individual intelligence, but all the agents should coordinate in a way, such a way that the system behavior meets global goals. We talk about collective intelligence. Autonomous systems are often critical systems intended to replace humans in complex organizations, as this is envisioned by the Internet of Things, and they are highly dynamic, reconfigurable systems that, for which also we have the problem of guaranteeing correctness at design time and runtime because of their evolutivity. Now, regarding the industrial acceptance of autonomous systems, I would say that the autonomous car sector is leading the way, but they have problems with trustworthiness guarantees, and acceptance in other sectors is more gradual. I think that to make this autonomy vision a reality, we need new theoretical foundations, and we need to work in two directions. In fact, we need to rejuvenate traditional systems engineering with hybrid design flows that will allow the integration of data-based and model-based techniques, and also seeking trade-offs between design time and runtime correctness. And also, I think that knowledge development and management will become something very, very important, in particular a factor that will help overcoming complexity and compensate the non-explainability of AI systems. Now, let me discuss a functional characterization of an autonomous agent by considering the autopilot of a self-driving car. So you see this is a reactive system. It receives sensor information, produces commands. It needs to achieve a situation awareness, analyzing, say, frames that come from sensors of the environment. So this is what is done by using the perception function that will analyze and find out the obstacles around the car, and this reflection function will build a predictive model of the world based on which we will make decisions, and decision-making means goal management. So self-driving cars have to deal with many different types of goals, perhaps more than 10 different types of goals, short-term goals, keeping the car on a trajectory, avoiding collision, and long-term goals. I am here, I'm driving to a destination. And for each active goal, we will start a planner that will generate commands. Now, this regarding the reactive behavior of the system, it's important to understand that agents should also exhibit some proactive behavior based on knowledge management. You see that here I have a memory where I have what I call a word model. It's knowledge about the environment of the agent and its own state. And this knowledge is very important. It is updated by this self-awareness module that permanently monitors the state of the agent and generates new knowledge. And also this module provides some predictions about parameters that are used here. I have no time to give more details about that. Just to give you an example, if, for instance, in front of me there is a truck, I can identify the type of truck, and I have stored the properties of this truck, then I can have better predictions here. For instance, if I know maximal acceleration or maximal speed. Now, it is clear that we cannot build agents today by adopting this architectural principle for many reasons. There are several complex limitations, complexity of perception due to the difficulty to interpret stimuli, complexity of uncertainty due to the non-predictability of the external environment, and complexity of decision. I said that autonomous agents deal with a big variety of goals. The goals are maybe subject to different timing constraints. If I cancel a goal, this change should be consistent with the already pursued goals. Now, designing an agent is not enough. Agents should be integrated in complex environments, and also they should be able to harmoniously collaborate with human operators. And this is not just a human-machine interaction problem. This is something we know from our experience with self-driving cars. Now, if you have a system with many agents, the agents should adequately coordinate. On the other hand, the coordination of the agents should not impede the achievement of the individual goals, and also the agents should collaborate, as I said, to achieve global system goals and demonstrate what I consider as collective intelligence. Probably you've seen in the news the controversies around the deployment of robotaxis in San Francisco. You may have robotaxis that are safe, but they may obstruct traffic. They may block police cars or ambulances. So just to finish where we are standing today regarding this vision about autonomous systems, if autonomy can be characterized as by two factors, situation awareness and decision making. So increase in situation awareness here, a single domain, multi-domain, and decision making for a single agent or a system of agents. You see that today we are still in the beginning. We are here. We are striving to build intelligent agents for self-driving cars in particular. And in the future, we would like to be able to build systems of agents that exhibit collective intelligence. And there is a long way to go. Now, something else that is important to understand is that today to build autonomous agents, we have two approaches that both of them are not satisfactory. On the one hand, we can we can apply traditional model-based techniques that can guarantee trustworthiness of the systems we build, but these techniques are defeated by the complexity and also the heterogeneity of autonomous systems. The other approach consists in building end-to-end machine learning-enabled solutions. These approaches are taken by some companies for self-driving cars, typically Waymo and NVIDIA. This is a huge neural network that is trained to drive a car. It receives frames and produces steering angle and braking signals. But of course, these solutions are not trustworthy enough, and I think that for the future, we should strive to develop hybrid flows, and the hybrid flows should be able to integrate model-based components, typically for decision-making. I think we have good techniques, and the database for perception to solve some hard optimization problems. And another very important challenge is how to integrate these solutions in electromechanical environments. We don't have techniques for this. Now, to finish this discussion about autonomous agents, I would like to discuss this trend to agent AI that is triggered by the advent of LLMs. There are many papers, many works that propose tackle this problem of building agents, AI agents. Here there are some trends. One trend is to move from monolithic end-to-end AI solutions to architectures where we have LLMs and world models. The idea of world model is very important. The purpose of the world model, this is knowledge used to estimate missing information that is not provided by perception or to predict plausible future states of the world. Also, another idea is that we need symbolic computation. Machine learning is not enough. There are two approaches for that. Some people believe that symbolic computation can emerge from learning with increasingly powerful machines, and the other opinion is that symbolic reasoning must be hard-coded from the beginning, from the outset. Now, I think that LLM provide a basis for building autonomous agents, but this is not enough. We need to link them to domain-specific knowledge. There are different approaches. One is to have LLMs grounded to symbolic agents, and you see a list of engines here. And the other approach I like very much is that we use world models stored in a long-term memory, and we integrate LLMs with these models in what we call a RAG architecture, retrieval augmented generation architecture. And in this example here, I show how we can use an LLM and a world model to generate a predictive world model. So I have a prompt here that I send to LLM, and LLM generates a first context that is enriched by using this retrieval mechanism through access to the world model. So here you have another enriched context that is sent to the LLM to generate the best possible context for the world model. Now, let me talk about validation of AI systems. Everybody understands the problem of validation. We want to have some guarantees that the system A satisfies a property P, The property P should be rigorously defined, and also we should provide a falsifiable validation method. This is clear. And there are, in fact, two techniques to do that. As you probably know, we can apply other verification techniques, and verification consists in comparing a model S against a model S of the system to be verified against some specification of this property P that we want to validate. And you know probably that verification is very, very important to get strong guarantees about system trustworthiness. In particular, you can examine in the model to find all examine the properties of the states. You can reason on the state space, and you can have a strong trustworthiness guarantees. Now, we know that for AI systems, we cannot have models that describe their behavior, and verification is hopeless. So the only solution is to go to adopt the testing techniques. Testing is also, we have well-established methods, testing methods. Testing is the basic of the scientific, the basis of the scientific approach to produce empirical knowledge. Of course, when you test, you are subject to observability and controllability constraints, and also you are limited to properties that can be that characterize the input-output relation. You cannot examine the state space, and the properties can only be falsified. So the important question is to what extent we can we can validate properties of AI systems by using testing. So let me remind you some very basic things about test methods. So in the test methods, I have a system S. So I'm giving here this relation between input and output. And the property, in fact, is a predicate, is a hypothesis that characterizes that this input and output behavior. So in a test environment, I will have the system, I apply X, I observe Y, I have an oracle that will evaluate this predicate and will give a verdict, a pass or fail. So I hope you are familiar with these ideas. Now, the test methods should allow you to choose the test cases. So it should tell you how to choose the test cases so that you should be possible to decide whether the testing process is successful or not. And usually a test method uses a coverage function and a score function. Coverage function is a function that measures the extent to which a set of test cases explores the characteristics of the system. So it's kind of probability that characterizes the way the set of inputs explores the behavior of the system, and the score function given a test set, so a set of inputs and the corresponding responses will estimate the likelihood that S meets P. Now, a very important constraint when you have such a method is reproducibility of the results. That is, if you have two test sets, and the coverage, the coverage of the X1 and X2 here, that are the sets of test cases is the same, then the score will be more or less the same, modulo some within some margin that can be estimated by theory. And this is something very, very important. I'm not going to give details here in this table. I show different applications of test methods in physics and software engineering, in medicine also, if you want to test the efficiency of a medicine. And here I'm considering different types of intelligent systems. What is clear is that for conversational systems like ChatGPT, you cannot formalize the property P, and the oracle, of course, is a human that can give only subjective judgments. So applying this scientific method to LLMs is hopeless. However, for other types of systems, as this one, or self-driving systems, this is possible if we have a theory about that, as I explained, and for the moment we don't have we don't have a good theory. And let me explain why. I've been working on this problem of testing self-driving cars for years. So probably you have seen this in the news. We've driven 10 billion autonomous miles in simulations, suggesting that their self-driving platform is safe enough. And it's clear that this argument is not technically tenable. Why? Because they don't explain how a simulated mile is related to a real mile. And for this, you need some theory, some analysis. You need a coverage criteria to explain the extent to which the simulation deals fairly with the many different situations that a car can encounter, different types of roads, traffic conditions, weather conditions, etc. And this theory is missing here, unfortunately. So there is a long way to go to develop validation theories for AI systems. Now, let me talk about the future. A very important question for the future is what is intelligence? What is an intelligent system? Okay, because this determines also the final goal of AI. I think that autonomous systems propose a multifaceted concept of intelligence. In fact, there are multiple intelligences. It's characterized by the ability to perform a task in a given context. So to say that system S1 is smarter than system S2 is meaningless without specifying the task and the criteria for success. Something else I would like to emphasize that human intelligence is not a theoretical concept. Computation is a theoretical concept. Human intelligence is the result of an evolution in a given physical environment. So if we were born on another planet, then our intelligence would have been different. Now, if human intelligence is the benchmark, is the reference, AI should be able to perform and coordinate a set of tasks that characterize human skills, in fact. Something else I would like to explain is that there is a complementarity between machine intelligence and human intelligence, as machine intelligence is today. Machines are very good at analyzing multidimensional data, and humans are not good at that. But humans are capable of common sense, abstraction, and creativity, as you know. So we can consider this space of possible intelligences, and we can imagine that somebody can combine the two types of intelligences. I think that this figure also poses some interesting questions about how we can bridge the gap between symbolic and concrete knowledge. Whether this is possible to do exclusively with neural networks, I don't think so, or I don't believe so. But there are some indications that by using LLMs, some problems that we solve by reasoning can be solved also by using database techniques. Okay, now let me move on to discuss another important problem that is the validation of AI systems. Today, there is a tendency to consider AIs are moral entities, in fact, and this is seems to be a way to avoid the debate on the validity of technical properties like safety and security and the application of scientific methods. What I would like to explain here is that unlike safety and security properties, ethical properties cannot be decided only on the basis of the agent's observable behavior. If I tell you that the earth is flat, this may be a lie, or it can be also the fact of ignorance, of or non-awareness that I'm doing something wrong does not imply my responsibility. So in order to decide the ethical properties, you should know what the agent knows, in fact. And this is a very challenging problem. I have no time to discuss this. Another important question regarding system validation is how we validate LLMs. So systems that deal with natural languages. I said that the technical, the rigorous approach is not applicable, but perhaps we can have approaches that are between the rigorous validation and also the qualification tests we apply to humans. So, for instance, somebody can imagine that we apply to that LLMs are able to pass final exams in medicine. Shall we accept the idea that an LLM who can become a medical doctor? Regarding this possibility, I have a few remarks here. First, there is a big difference between LLMs, neural networks, and humans. Human thinking is robust, while neural networks are not robust. We know this, okay? And human thinking also is based on common sense knowledge, so humans are better placed to avoid inconsistencies that that are produced by LLMs. And also humans are responsible for the consequences of their actions and omissions, and of course you will not put a system in jail. So to conclude, I will say that it's very important to avoid superficial debates about ethical properties of AIs in absence of rigorous characterization of these properties. And also, I think that we should strive to overcome current limitations by developing new foundations, possibly revising some epistemic and methodological requirements in a wise manner, finding a good compromise. Now, something else that will become very important is the marriage between AI and systems engineering. We would have AI systems in any artifact. And today we see new trends that are disrupting traditional systems engineering. I said that we are adopting end-to-end machine learning-based solutions for self-driving cars. We have this trend of self-certification in the United States in absence of standards, and also they allow regular updates of critical software in Teslas, for instance, and this is against the standard practice. So for the future, I believe that we should strive to develop hybrid design flows, and here the challenge is how to link symbolic and database knowledge. Of course, I think we should try to get around the non-explainability obstacle, but we should figure out techniques that give trusted systems from trusted components. We have some solutions for that. And of course, we should strive also to develop AI systems that are more safe by adopting restrictions on the training data sets, to have better predictability and controllability. When an LLM explains how to make a bomb, it sums up information acquired during the training. So this should be avoided somehow. Also, system validation is marked by this shift from rationalism to empiricism, as I said. So random testing is not enough. We should develop some techniques, probably based on statistics, for validation of AI systems. Of course, we will not have the strong trustworthiness guarantees we get with traditional methods, but this weakness can be offset by the use of knowledge-based techniques. So to summarize, the transition from automation to autonomy cannot be progressive, it will take some time, and we need some new scientific and engineering foundation. To finish, I would like to discuss very quickly the risks from AI and the regulation. Clearly, there are two types of risks: technology risks from hazards compromising an AI's ability to meet safety and security requirements, and human risks And human risks can be regulated by legal frameworks. We know this. For instance, if an LLM can generate deepfakes, and this can be considered as a technological risk, its use can be prohibited by law. Now, something else I would like to emphasize here that despite all the official statements from governments and institutions that we need AI regulations, there is no agreement about how these risks what are these risks, how these risks can be regulated, and how this can be achieved in practice. So, to conclude, I will say that there is a gap between European Union and US concerning the AI regulations. AI has, EU has a strong and very complete AI regulation framework. I will mention the AI Act here, and the US regulations are more permissive. And I think the chances of reaching an agreement on a global regulatory framework are very slim today. So let me stop here and thank you very much for your attention. Thank you.